Hey everyone, and welcome. I am absolutely thrilled to have you here today. In this explainer, we're taking a journey into the hidden, rigorous, and frankly just fascinating world of construction testing. Every single day, we walk into massive structures, drive over towering bridges, and live in our homes without giving a second thought to the ground they stand on or the materials holding them together. But the truth is, a building's safety isn't guaranteed by an architect's sketch. It's earned through an exhaustive, relentless series of scientific tests. So we're going to strip away the drywall and look at the bare bones of building safety. Think about this for a second. How do we actually guarantee that a 50-story skyscraper doesn't just sink into the mud? Or that its concrete walls don't crumble under that immense pressure? It's almost a miracle of modern engineering, isn't it? But here's the secret. Safe buildings aren't just built, they are relentlessly tested, from the very dirt they sit on all the way up to the roof. You see, engineering is all about proving, mathematically and physically, that failure is simply not an option. Okay, let's dive right into this. We're going to follow a chronological, ground-up blueprint for this explainer. We'll cover 1. Understanding soil before building. 2. Preparing and supporting foundations. 3. Testing fresh concrete. 4. Strength of hardened concrete. And 5. Protecting structures from corrosion. Section 1. Understanding soil before building. Let's look at what lies beneath. Our first critical phase takes us right to the ground level, or well, actually below it. Before a single brick is laid or a trench is dug, engineers have to know exactly what they're dealing with, because the strongest concrete in the world is totally useless if the ground beneath it gives way. Using a process of sieves and sedimentation, they separate the earth into exact categories based on the unified soil classification system. Is the site resting on gravel, sand, silt, or clay? They literally sift through the dirt, washing and baking samples in a lab to classify the exact composition. If it's clay, it might expand with water. If it's sand, it might shift. Knowing this dictates every single engineering decision that follows. So once we know what it's made of, we need to know how strong it is. This brings us to the Standard Penetration Test, or SPT. And let me tell you, this test is both beautifully precise and wonderfully brutal. First, crews drill an exploratory borehole deep into the earth. Then, they take a massive 63.5-kilogram hammer, that's roughly 140 pounds, and they drop it from a very specific height of 76 centimeters. They repeatedly slam this hammer down to drive a sampling tube into the earth. What they're looking for is exactly how many hammer blows it takes to push that tube through the final 30 centimeters of soil. Now, what's really interesting about this is how engineers translate those violent hammer blows into a hard mathematical truth known as the N value. If it only takes 0 to 4 blows, that ground is practically mush, very soft and loose. You definitely can't put heavy foundations on that without serious intervention. If it takes 10 to 30 blows, you're looking at a medium, stiff, dense soil. But if you have an N value over 50, that soil is very hard, very dense, and has incredible load-bearing capacity. That single N value tells the engineers exactly how heavy a building the earth can safely hold. Moving on to Section 2, Preparing and Supporting Foundations, which is all about compacting the ground. Moving right along our construction timeline, even if the soil is fundamentally good, once the site has been disturbed, it's full of air pockets and has to be compacted. And to understand exactly how to pack it tightly, engineers rely on the absolute gold standard, the Proctor test. You can't just run over dirt with a heavy roller and hope for the best. Soil is tricky. If it's too dry, the particles won't slide together. If it's too wet, the water actually holds the particles apart. The Proctor test is a lab process that finds the perfect, absolute sweet spot, the optimum moisture content that allows the soil to reach its maximum dry density. It gives the construction crew on site the exact benchmark they have to hit. But how do we know the crew actually hit that benchmark out in the field? Well, enter the sand cone test. Site engineers will dig a small hole right in the compacted dirt, weigh the extracted dirt, and then fill that hole back up with a highly uniform, pre-calibrated sand. Because they know the exact weight and volume of this testing sand, they can calculate the actual density of the compacted ground. If the site crew didn't hit a compaction ratio of 98% or higher compared to that original Proctor benchmark, they have to water the dirt, roll it, and compact the whole thing all over again until they get it perfectly right. Section 3, Testing fresh concrete. Let's talk about the window of workability. This brings us to a highly stressful, tightly scheduled phase on site, the race against time with fresh materials. I mean, imagine trying to pump wet concrete 30 stories up into the sky. How do engineers prevent that concrete from drying too fast and instantly jamming up those massive mechanical pumps? But conversely, how do they ensure it's not so watery that it completely loses its structural strength? Well, the answer lies in a deceptively simple metal cone. This is the slump test. Right as the concrete truck arrives, technicians fill this cone with fresh concrete, pack it down, and then just lift the cone straight up. This single, simple action reveals everything they need to know about the mix's moisture and workability. The way the concrete behaves when that cone is lifted is absolutely critical. Basically, we're looking for one of three visual outcomes. A collapse slump means the pile just falls apart completely into a puddle. The mix is way too wet and structurally weak. A shear slump slides awkwardly off to one side, which means the mix lacks cohesion, the rocks and the paste are actually separating. But a true slump, that drops evenly, settling just slightly while holding its overall shape. Only a true slump guarantees that the concrete is perfectly balanced and safe to pour into the building's skeleton. And the magic number they're trying to measure? A drop of 75 to 150 millimeters. When you have heavily reinforced structural elements like columns and beams, those spaces packed tight with steel rebar, you need the concrete fluid enough to flow into every tiny corner without leaving dangerous air pockets, but stiff enough to retain its monumental strength. This 75 to 150 millimeter slump is that perfect Goldilocks zone. All right, Section 4, Strength of Hardened Concrete. It's time to see how it handles the pressure. Fast forward a bit. Weeks have passed. The poured concrete has dried and hardened. But we aren't done, not by a long shot. We now have to prove, without a shadow of a doubt, that it can actually bear the crushing weight of a skyscraper. Engineers use a really clever two-pronged attack here, lab precision versus on-site reality. First up is the cube test. While the concrete is being poured on site, technicians cast perfectly square 150 millimeter cubes and cure them in ideal temperature-controlled laboratory conditions for 28 days. This proves the mix design itself was correct. But the real world isn't a lab. If there's any doubt at all about how the concrete cured out in the hot sun or the freezing wind, engineers run the core test. They use specialized diamond-tipped machinery to drill actual cylindrical cores right out of the finished hardened columns on the site. Whether it's a lab cube or a site core, the destination is exactly the same: the crushing machine. The sample is placed into a massive hydraulic press that applies hundreds of thousands of newtons of force. It is a dramatic, almost explosive moment. The machine measures the exact point at which the concrete catastrophically fails, and they're looking to hit incredible targets here, often 30 megapascals or more, depending on the building code, just to ensure that the concrete can hold up the dozens of stories towering right above it. And this brilliantly illustrates a super fascinating aspect of material science. How the concrete breaks in the machine is just as important as the force required to break it. Engineers closely analyze the fracture patterns of the rubble. A conical shape from top to bottom means the load was perfectly distributed. That's a good test. Vertical splits or columnar cracking are also generally acceptable. But if they see a shear fracture where the block just sliced and slid to one side, that is completely unacceptable. It means the test itself was flawed, likely an issue with friction on the machine's plates or maybe an uneven surface on the sample. And if the break is wrong, the data is entirely useless. Finally, Section 5, Protecting Structures from Corrosion. Time to face the invisible enemy. Okay, so our foundation is solid, our concrete is impossibly strong, but we have to ensure this pristine structure survives decades of environmental attacks. Concrete looks completely impermeable, but at a microscopic level is actually porous like a sponge, and the ultimate silent killer of buildings is chloride ions, essentially salt. Whether it comes from salty ocean spray in a coastal city or from contaminated sand accidentally used in the original mix, chloride seeps right through the concrete and attacks the internal steel rebar. It rusts the steel, causing it to expand and literally blow the concrete apart from the inside out. To hunt down these salts, engineers perform the chloride content test, extracting fine dust from deep within the concrete core and testing it chemically. And the margins they operate on here are shockingly small. According to strict building codes like the ACI 318, anything under 0.05% chloride by weight is considered safe from corrosion. From 0.05% to 0.15%, you're in the acceptable range, but you definitely need to keep a close eye on it. Once you pass 0.15%, the risk becomes critical. And anything over 0.3% is a severe risk of structural failure over time. So the crucial takeaway here is that even a tiny fraction of a single percent of salt can spell disaster for a building's lifespan. That's why this testing is so utterly vital. As we wrap up this journey through the hidden world of construction engineering, I want to leave you with this summary philosophy. Safe buildings aren't just built, they are relentlessly tested. Engineering isn't simply about creating an awe-inspiring design on a computer screen. It's a constant, meticulous, and continuous battle against nature, against gravity, and against time itself. From pounding the dirt with hammers to crushing concrete cubes and hunting for microscopic salt, every single test is a layer of defense. So, the next time you walk into a towering skyscraper, step onto a massive concrete floor, or look out a window hundreds of feet in the air, I want you to ask yourself, how many unseen tests, how many crushed cubes, and how many incredibly precise calculations did it take to make this single step safe? It's a true testament to the incredible rigor of the people who test our built world. Thank you so much for joining me in this explainer. Keep asking questions, keep looking past the surface, and I'll see you next time.